Thanks for the invitation, and it's my pleasure to present my work here. So I'm going to talk about the closest pair problem and the quantum upper bound and lower bound for this problem in different scenarios. So this is the joint work with Scott Aronson, Naihui Jia, Han Xuanling, and Richard Zhang. So this is the arXiv number. If you want to read the full details, you can find the full paper there. So let me start by state the problem, the closest pair problem. So we're given, the problem is very straightforward. So we're given an endpoints in some d-dimensional space, and we want to find the pair with the smallest distance. So here, the two parameters are very important. N is number of points, and d is the dimension. So in this case, n is I don't have time to count the number of points, but d is 2, the two-dimensional space. It's just plain. So of course you can have the problem in a three-dimensional space or even higher dimensional space, but I don't know how to draw a four-dimensional space in using my computer. So okay, so in this example, this pair is the closest pair we need to find. Okay, and this problem has many applications. For example, data analysis, clustering, and point location. So I don't care about the applications here. So I only care about how fast you can solve the problem. So classically, what you can solve the problem naively, you can use. I think the most straightforward approach is the brute force search. You search for every pair, you check every pair, and find the smallest distance. Then the cost is n squared because you need to, there are roughly n squared pairs. Okay, and you can do something more smarter. You can use divide and conquer algorithm, and then that's taught in algorithm textbooks. So if you don't have computer science background, or if you haven't taken the algorithm design course, I'll briefly show this divide and conquer algorithm. So the idea is like this. You first divide the points into halves. Then you recursively find the closest pair from the left-hand side, and also find the closest pair on the right-hand side. Okay, suppose the smallest distance from the left-hand side is delta 1, the right-hand side is delta 2. Then there are three possibilities. The first, delta 1 is the smallest pair of all the points. Second, delta 2 is the smallest pair. Or the closest pair is crossing the boundary. Okay. Then the third case is very interesting. So we need to identify it. So let delta be the minimum of delta 1 and delta 2. Then to check the boundary case, we define the strip, delta strip along the just on the two sides of the boundary. Then for each pair in the strip, we only need to check constant number of neighbors. Then we just check the constant number of other points. Then we can do this. So if you work out with the recurrence relation, you can know that the time complexity of this divide and conquer is n log n. And this approach only works for constant dimensions, because for higher dimensions, this checking part takes a lot of time. Then for higher dimensions, the best known approach is to do brute force search. Okay? So for higher dimensions, you even you do whatever trick you know, then it's always slower. It's always no better than this brute force search n squared algorithm. So here are some lower bounds for this problem. So when the dimension is constant, in the late 80s, Yao proved that this the lower bound is is almost linear. It's here the tilde hides the polylog factor. And when the dimension is higher, very recently, Karthik and Manarasi showed that the lower bound is almost quadratic. So, but their lower bound is conditional. It's based on this hypothesis called strong exponential time hypothesis. So this hypothesis was proposed by Impagliazzo and Paturi in 2001. So this SETH is saying that basically it's saying that you cannot solve K-set faster than 2 to the n time. Okay. So and this hypothesis is very plausible. And after years of work, people haven't found any algorithm to solving K-set in general faster than 2 to the n. Okay. So that means for the closest pair problem, that means in higher dimensions, the best we can do is to use brute force search because of this near quadratic lower bound. Okay. So if you believe Q-set, then in higher dimensions, the best thing you can do is to do brute force search. And so this is summary of what we knew and what was known and what was unknown. So when dimension is constant, we knew everything except for the quantum upper bound. So for quantum lower bound, in 2004, Aronson and Shi proved the n to the 2/3 quantum lower bound. This lower bound was for the element distinctness problem, but it also applies to the closed pair problem because element distinctness is a special case of closed pair. You can think element distinctness is just one the closest pair on a line. Okay, so the lower bound still applies to the closed pair. And when the dimension is higher, we knew everything except for the quantum lower bound. And the quantum upper bound is trivial. You just, because we know we have the brute force search algorithm, then you just apply Grover. You get near linear quantum upper bound. But we didn't know the quantum lower bound. Okay? So the contribution of this work is that when the dimension is constant, we gave a quantum algorithm to solve the closed pair problem using n to the 2/3 time complexity. And this is almost, this bound is tight up to polylog factors. Okay? And also when the dimension is higher, we showed that the quantum lower bound is almost linear, and means that this Grover search is almost the best you can do. Of course, our lower quantum lower bound is also conditional. It depends on it relies on a quantum version of SETH. I'm going to talk about the quantum version of SETH later in this talk. Okay, so in the next, I will first say something about the upper bound. I will show the quantum algorithm. Then after that, I will talk about the lower bound. But before we talk about this n to the 2/3 quantum algorithm, let's do some warm up. Let's give n to the 3/4 quantum algorithm. This is slower than n to the 2/3, but it's still better than linear. Okay. Okay. Suppose you are given. Okay, this works in constant dimensions. Suppose you are given this endpoints. The first step is to partition these endpoints into square root n colors, and each color contains roughly square root n points. Okay? Then the next step is to pick a random anchor color. Pick an anchor color uniformly and random. Let's say we pick red. So we hope the either of the two possibilities is true. The first is that the closest pair is within red, or the closest pair is between red and other colors. We hope either of this is true, but otherwise we can repeat to pick another anchor color to repeat the following steps. Okay, so suppose we have red as our anchor color, then the first thing to do is to find the closest pair within red. So this, using brute force search, it takes linear time because each color has a square root n points. Okay, so to do this, the cost of this step is linear in n. But you can use Grover to get to do this in square root n time. Then, then we need to check the pair between red and other colors. To do that, we need to build some data structure to support this, to support nearest neighbor search. So we built a data structure of the red points. For example, we can use the Voronoi diagram. The Voronoi diagram supports nearest neighbor search. The time to build this data structure is square root n log n. But once you have the data structure, to find the nearest neighbor for any given point, it only takes log n time. So once you have this data structure, you can very efficiently find the nearest neighbor for any given point. Okay. Now, because of this data structure, finding a closest pair between red and other colors takes n log n time, because there are n other points, and each query takes log n time. So this is the cost for this step, n log n. But you can use Grover to get roughly square root n speed up for this step. Okay. So now we assume that either the closest pair is within red or is between red and other colors. So what's the probability of this can happen? The probability is that at least one point is in red. The probability is 1 over root n. Okay. So that means if this is not the case, then we can just repeat this. We can just choose another random color uniformly and random, and we repeat. So it means because of this probability, we need to repeat roughly square root n times to succeed. But we can use a variant of Grover search, which is called amplitude amplification, to boost this, to reduce the square root n repetition to like n to the 1/4 time. Okay, so that means we just it's not repeating, it's just you just need one n to the 1/4 time to achieve this. Okay. So the total time complexity is this. Is the number of is the square root n, which is the cost for each step, times n to the 1/4, which is the number of repetitions. It's n to the 3/4, n to the 3/4. Okay, so this is the very simple quantum algorithm for the closest pair problem. It's faster than it's faster than linear, but it's not the best we want. Okay. Now we are working on this n to the 2/3 quantum algorithm. But before that, let me introduce some concept called Markov chain search. So suppose we have a Markov chain. The Markov chain is just is some random walk on a graph. So this Pij is the probability of jumping from I to j. And if you write all the Pijs, it's a stochastic matrix. So in this Markov chain, some vertices are marked. So I use this red to denote marked vertices. Okay. So the problem is, how do you find a marked state in this Markov chain? So first, the first step to do this is to sample a state from some distribution. So usually we sample from the uniform distribution of all the states. Okay. Then you walk. You just perform the random walk. You walk until you get mixed. By getting mixed, I mean the distribution is approaching to the stationary distribution of this Markov chain. Then you check if the current state is marked or not. If marked, then we're done. Otherwise, you just keep walking until next mixing, and then you check. So what's the time complexity for this Markov chain search? It's given by this formula. So let me explain the parameters. So here, epsilon is the fraction of marked vertices. Delta is the spectral gap of the Markov chain, and U is the cost for taking one step, and C is cost for checking. Okay, so basically the thing in the parenthesis 1 over delta U is roughly the 1 over delta is roughly the number of steps you need to take until you get mixed, and 1 over delta U plus C is this cost. Is the cost for walking until mixed and checking. Okay, and then this 1 over epsilon tells you how many times you need to repeat. Okay, so it's very intuitive that this formula gives you the running time of this Markov chain search algorithm. Then for the quantum algorithm, we need to quantize the Markov chain. So there are different quantizations. But we use this the quantization proposed by Zechty in 2004, which is the quantum walk. So in this slide, I would define what the quantum walk operator is looking like. So here, for each vertex I, we can define this psi I as two registers. The first register contains the I itself. The second register contains a superposition of all the neighbors. Okay. Then we can define this projector like this. And we also have the swap operator that will swap the first register and the second register. Then the quantum walk operator is like this. So the most any questions? I heard some voice. Is it a question? Okay, if now I will go on. Okay. So this is the quantum walk operator. So the most important thing to analyze a Markov chain is to analyze its spectral gap. Also, we also need something like spectral gap for this quantum walk operator. But it will take another lecture, so I won't do this. So I will just show you what the quantum operator look like, and the quantum walk search is based on this. This is the building block of the quantum walk search, which is this. So if we use the quantum walk to do the search, so remember this is a classical cost. So what's the quantum cost? The quantum cost is to take square root of the epsilon and also take square root of delta. And this quantum walk search framework was proposed by Magnus, Nyack, Roland, and Thansa in 2011. So this is a very nice algorithm to using quantum walk. I'm not going to open the black box of this quantum walk search algorithm, so you can use this as black box in the rest of the talk. Okay. So let's see how to use the quantum walk search to solve the closest pair problem. Suppose the dimension is constant, then we first consider the decision version of the closest pair. The decision version where we need to determine whether there exists a pair of distance smaller than epsilon. So yes or no. If we can solve the decision version, then we can use binary search to find the closest pair. Okay. So to solve this using Markov chain search, we first convert this the closest pair to a Johnson graph. Okay. For the Johnson graph, J of parameter n to the 2/3 is like this. So n is number of points in for the closest pair problem, and each vertex of the Johnson graph contains n to the 2/3 points. So for example, in this example, n is 8 and n to the 2/3 is 4. So each vertex of the Johnson graph contains 4 points. Okay, and the two vertices are connected if and only if they differ by exactly 1 point. So for example, for here, this point is 1, 2, 5, 7. This is 1, 2, 4, 5. So they differ by 1 point. So we connect them, and we connect other vertices by the similar manner. And this is only part of the Johnson graph. The original Johnson, the whole Johnson graph can be very large. Okay? And there are some marked vertices on the Johnson graph. So we marked vertex if and only if they contain a pair of a distance smaller than epsilon. For example, if in the closest pair problem, the distance between 4 and 5 is epsilon, then we mark this and also mark this. So okay, so the problem of here reduces to this: how do we find a marked vertex in the Johnson graph? Okay? If we can find a marked vertex in the Johnson graph, then we can answer this. We can answer this decision version problem. And we can we find the marked vertex by random walk search. So here gives the query complexity. So I'm talking about query complexity because I don't care about the implementation now. So later I will talk about the issue of the implementations. So here, the fraction of marked vertices here for the Johnson graph is n to the minus 2/3, and spectral gap for the Markov chain is also n to the minus 2/3. And if you plug the numbers in the formula, you will get n to the 4/3 query complexity for doing the random walk search on the Johnson graph. Okay. So if we use the black box for quantum walk search, we can get this quantum query complexity, which is take square root for the epsilon and the square root for the delta. We get n to the 2/3 quantum query complexity. Okay. It seems we're almost done because we get the number we want, n to the 2/3. But no, it's not finished yet, because this is the query complexity. We need to talk about the time complexity. Then by talking about the time complexity, we need to worry about how to implement this algorithm, and what's the cost for taking one step, and what's the cost for checking. Okay, so if you use the trivial implementation, I mean, if you just store all the points in a list or something like that, then update should be efficient. But checking is time consuming, because for checking it, if each vertex is marked or not, you just basically check each pair. Okay? Then because each vertex contains n to the 2/3 points, then checking each pair costs n to the 4/3. So if you plug these numbers back into the formula, the time complexity will blow up. So this implementation is certainly not good. So actually, we need to define some data structure. We need to design some data structure to support this efficient update and checking. So our goal is to have some data structure with polylog update time, but constant checking time. And more importantly, this data structure should be history independent. That means the representation of this data structure shouldn't depend on the order of the insertion deletions, because otherwise the quantum interference will be destroyed. So, for example, if for this vertex 1, 2, 5, 7, if the insertion and deletions the order of the insertions and deletions are different, then maybe in the execution of the quantum algorithm, the same state will have different representation. And actually, it should be the same state, but because of the data structures are represented differently, and then they become different states. But at some point, by the quantum interference, we might expect them to cancel each other. But because they are different, so they cannot cancel each other. So the quantum algorithm will give you the wrong answer. So that's why the history independence is very important here. So to overcome this, so we use this, we define this data structure. It's somehow complicated. So the first thing we do is to discretize the space into grids. Okay, so some points, some grids are empty, but some grids are containing 1 point or more than 1 point, and the grid size is epsilon over square root d. So by this grid size, we know that if 2 points are in the same grid, then it's within the distance is smaller than epsilon. And also for each grid, we only need to check constant number of neighbor grids to see if there's a pair of if there's a close pair or not. So how do we organize the non-empty grids? We use this radix tree. A radix tree is a data structure of organizing something where it's a binary tree where the edges are labeled by some zeros and some binary strings in the way that if you follow the path from the root to the leaf, then the label, you concatenate the labels on the edges, you get the key of the leaf. So here we use the grid ID, the ID of the grid as the key. Okay. So the radix tree has a nice feature is that the radix tree is history independent. No matter how in what order you insert or delete these leaves, then you will also have the same radix tree. So now we need to check if a grid contains more than 1 point, or we also check the neighbor grids. If we find a close pair, then we mark this leaf. We also mark this ancestors. Then at the end of the day, if you just check the root of the radix tree, you will know immediately whether or not you have a pair of distance smaller than epsilon. Okay. So this is how we organize the grids. But there are multiple points. There can be many points inside a grid. So we also need to organize them. We need this. So first we need a hash table to store all the points. Okay, the hash table serves the purpose of a memory. Okay, we kind of use the hash table as memory. Then we inside each node, inside each grid, we use the skip list to store the points inside the grid. The skip list can support the skip list is a randomized data structure, so the expected time for checking for search is log n. So so by this we can by using the skip list we can quickly check we can quickly locate a point in a grid. Okay. So by the combination of radix tree hash table and the skip list, there are of course some more complicated details behind this data structure, but the ideas is the rough idea is the 3 components. Then we use the combination of the 3, we can get this desired update time and the check-in time. Okay? And if you plug the numbers inside this formula, you will get this n to the 2/3 time complexity. So this is what we want. So this is the quantum upper bound. So this basically this strategy tells us that when we are looking for quantum speed ups, we don't need to focus on the best classical algorithm, right? Because for example here, if we actually based on this the random walk search, if you check the random walk search, is not the best classical algorithm. The best classical algorithm is n log n, but here is larger than linear. But if we based on this, and we can get some quantum speed up. So we actually in many cases when we look for quantum speed up, we don't need to target on this we don't need to target on quantizing the best classical algorithm. We can find the other way to get some better quantum algorithms. Okay. So this is the end of the upper bound part. So let me talk about this the lower bound optimality when the dimension is higher. So so recall that this classical lower bound is this relies on this SETH, and they showed Karthik and Manarasi showed that if you believe SETH, then the closest pair has the near quadratic lower bound. So likewise, we propose this quantum SETH. The quantum SETH is saying that you cannot solve a k-set faster than n to the 2 to n to the n over 2. So that the quantum SETH basically saying that the best you can do, the best you can hope for solving k-set quantumly is using Grover, okay? Because this is Grover speed up. So our result is that if you believe Q set, then we can show that closest pair has quantum lower bound that has this near linear quantum lower bound. Okay. So in the following, in the rest of the talk, I'm going to, I'm not going to show the details of this how we get to the lower bound, but I'll give you some ideas, and also introduce some this fine-grained complexity. Okay. So this reduction uses the idea of fine-grained complexity. So if you have some computer science background, if you take the complexity theory courses, you know the polynomial time reduction. The polynomial time reduction is that suppose you want to solve algorithm A, but actually you can use the black box for problem B to solve A. Okay, so the first thing you do is to given some instance of A, you have some pre-processing algorithm R to pre-process to convert the instance of A to instance of B. Then you use the black box for B to get some solution for B. Maybe here you need some post-processing to convert the solutions for B back to the solution for A. Okay? Then, so the idea of this polynomial time reduction is that if the pre-processing is polynomial, and we know that if there exists a polynomial time for B, it implies there exists polynomial time algorithm for A. Okay, so the contrapositive form of this statement is that if A is hard, then it implies B is hard. So in this polynomial time reduction, we just need this time to be polynomial, and we don't care how large the polynomial can be. Okay, so in some sense this is very coarse-grained. So for the fine-grained reduction, we do care about this polynomial here. Okay, suppose the polynomial is R of n. So the fine-grained reduction is saying that suppose there exists a Qn time algorithm for B, then there exists Qn plus Rn time algorithm for A. Okay? So this is this fine-grained reduction. It means that if A has the lower bound Rn plus Qn, then it implies B has a lower bound Qn. So we use this fine-grained reduction to prove some lower bound, fine-grained lower bound. Okay? And this for example, for this lower bound, we can use the SETH. So let me give you some example of this fine-grained reduction. We want to fine-grained reduce K-set to OV. OV is orthogonal vectors problem. Let me define the problems. So I think you are familiar with K-set. K-set is a Boolean formula satisfiability problem. Okay. So you're given the formula in a CNF form. You're asking if this formula is satisfiable or not. So for example, this is satisfying assignment. Okay. So K-set is okay. So let me introduce this problem, orthogonal vectors. So it takes two parameters, n and d. N is the number of n's number of vectors and d's dimension. Okay. So in this orthogonal vectors problem, we have two sets, A and B. The sets in each set, A and B, we have n d-dimensional binary vectors. Okay, so A1 up to AN. So each of them is a d-dimensional binary vector. Also for B1 up to Bn, for B1 to Bn, each one of them is d-dimensional binary vector. So the question is, can you find a vector in A and a vector in B so that they are orthogonal? Okay. So the goal is to use fine-grained reduction to reduce K-set to this orthogonal vectors. So that means if you believe as ETH, then this orthogonal vectors problem has this n to the 2 minus beta 1 lower bound. Okay, and we'll also extend this. We'll also quantize this to get quantum fine-grained reduction to conclude that if you believe quantum as ETH, then this problem also has a quantum lower bound, a near linear quantum lower bound. Okay. So let's see how this reduction works. So this reduction was first proposed by Williams in 2005. Suppose you are given this formula and phi 1 up to phi m, they are m clauses. So we assume there are n variables and m clauses. Here m is in the same order of n. Okay, so we define two sets A and B. A is the first half of variables and B the second half of variables. Okay, so this so far so good. Then we define the two sets SA and SB. So SA is all the assignments to A, and SB is all the assignments to B. So SA contains 2 to the n over 2 elements, and SB also has 2 to the n over 2 elements. And now we define this function FA and FB. So FA takes an assignment as input, and it outputs an m-dimensional vector. So binary vector. Each entry of the vector is just the negate of this clause evaluated on this AI. Okay. So, and likewise, we define the function FB. So we define two sets, FA and FB. FA are all the values of little FAs, and the capital FB contains all the values of little FBs. Okay. So this might be fast, but if you just stare at this these definitions for like a minute or 2 minutes, you will be convinced that if you have orthogonal vector on FA and FB, then it implies this formula is satisfiable. Actually, this implies this is if and only if. Okay. So what's the reduction time here? So here we reduce this K-set to orthogonal vectors. The reduction time, the bottleneck is here because we need to compute all the elements of FA and the capital FA and the capital FB. So the reduction time is huge, is theta n times 2 to the n over 2. So it means if we conjecture the lower bound for orthogonal vectors to this, if we conjecture the lower bound is 2 to the n times 1 minus little o1, then because its r is smaller than this one, this conjecture lower bound, so we have r plus this guy is still this guy. Okay. So if we look at the previous slide, if you plug everything into the previous slide, you will know that if k set has 2 to the n times 1 minus little o 1 lower bound, then it implies this orthogonal vector has this 2 to the n 1 minus little o 1 lower bound. So, but if you switch this variables, you will know that it implies this orthogonal vectors of n vectors of log n dimensions has this almost quadratic lower bound. Okay, so this is an example of classical fine-grained reduction. So we based on some plausible plausible assumptions as ETH, we get some conditional lower bound for the orthogonal vectors problem. So
you only have 5 minutes left, so maybe you can wrap
up. Sure. Yeah. So for the quantum fine-grained reduction is we can just quantize the classical fine-grained reduction. First of all, we use this oracle R. We use this for R. We use oracle, and for this guy we can use superpositions, and for B we use quantum algorithms. It implies that if there exists Qn time quantum algorithm for B, then there exists Qn plus Rn time quantum algorithm for A. Okay, that means if A has this quantum lower bound, then B has this quantum lower bound, and this lower bound can be obtained by the quantum SETH. So this is an example of quantum fine-grained reduction from k set to orthogonal vectors. So it might be hard to distinguish this slide from this slide, but I highlighted the differences. Basically, the reduction time is lowered because you just need to realize this small fa and small fb as quantum oracles. Then you can query in superpositions. You don't need to compute everything. So that's the significant part. Then it implies that if your k set has this lower bound, then it implies that orthogonal vectors has this near linear quantum lower bound. So this assumption is exactly quantum SETH. So this roadmap for the quantum lower bound for CP for closed pair, we need to define this bichromatic closed pair. So it's exactly like closed pair, but we have two colors. We need to find the closed pair between two colors. And the roadmap is that we first fine-grained reduce k set to orthogonal vectors, and then we fine-grained reduce orthogonal vectors to bichromatic closed pair. And then we reduce this bichromatic BCP to closed pair. We already saw this. But for this part, we can all. I won't show the details of this reduction, but it's always possible to quantize this classical reduction here. So this is the summary of the talk. So we basically fulfilled some unknowns. We get the tight upper bound and lower bound for different dimensions, and we propose the quantum version of SETH. And I'm happy to take questions. Thank you so much for your attention.